So, welcome to a new lesson where we're going to learn about compound interest. And this is probably one of the most important lessons you're going to have in your life because it'll show you how you can be a millionaire when you retire by letting your money and your time work for you. And the whole key to that is a very basic understanding of exponential growth. So, let's dive in. You've got some guided notes, and it is a good idea to pause the video throughout so you can get caught up on notes, so you can try some problems yourself. I have a couple problems at the end of this video that are not in your notes, so you may want to take some time and write them down so you have examples. Figure out what you need to do so you can be successful. So let's start out the whole idea with a problem. And this problem is that you have $5,000 somehow, and you have found an account some way that earns 10% APR. That abbreviation APR stands for annual percentage rate, which means 10% a year. And after 10 years, you want to know how much you're going to have if you compound it annually. Now, this is a great time to pause the video and to go to your guided notes and to read all about what these words mean. So pause the video, read what's written up there in the top, and then when you're done and you're ready to deal with year one, come back to the video. All right, well, let's take a look at what's going to happen in the first several years. In year one, we're going to start out with our $5,000 that we have. That's our principal. And we're going to multiply it by 10% interest rate. And that's going to last for a year. And that ends up giving us $500. Now, that's not how much we have in our account. That $500 is how much interest we have. So the next year, we have not $5,000 in our account, not $500 in our account, but the original $5,000 plus the $500 interest. And that year, we get to earn 10% interest because this interest is being compounded annually. Every year, you figure out your interest, and then that interest goes into your lump sum, and the next year, you figure out your interest on the new lump sum, which is your original amount and your interest. So after year two, we end up with $5,500. That money goes back into the pot. We now have $6,050 in year three. We calculate the interest in year three. We end up getting $605. And this goes on and on and on. And why don't you pause the video and see what happens by the time you get to year 10. All right, welcome back. Year 10, how much do you have? You have $12,968.71. That's money that your $5,000 turned into. Basically, you got about $8,000 extra in interest. Not by working harder, not by working more hours, but by putting the money into an interest-bearing account and letting it sit. Oh, well, actually, you did do a little work. You found an account that compounded your interest annually. Had you just put it into an account that compounds your interest in a simple way, you would have ended up with $10,000. So basically, by finding an account that allows you to compound your interest more frequently, annually, you were able to get an extra $3,000. It's a pretty good deal. Well, let's figure out how this works. Let's see how this ended up giving us so much money. And maybe we can use this to develop a formula. So we're going to step away from our notes for a second. You don't need to write this part down. I just want you to follow along and see if it makes sense. So let's get started and think about what happened at year one. At year one, we took the $5,000 and we multiplied it. Now, by 10%, and that gave us the interest. But I'm going to multiply it by 1 plus 10%. Because this time I'm not calculating the interest. I want to calculate the total amount of money that we had at the end of that year. Both the interest and the original amount. So you see, when you distribute, you get your original $5,000 plus your interest. And then what happens in year 2 is we have whatever we were left with at the end of year 1, this total amount here, and we find the interest on that. And that gives us a new amount. What happens in year 3? Well, in year 3, we take all of what we had in year 2, which is this 5,000 times this, and then we multiply it by another 1 plus 0.10 because we're calculating the interest for a new year. In year 4, we take, the whatever we had in year 3, this whole big amount, and we multiply it by another 1 plus 0.10 because it's a whole new year. We find a whole new interest on that. And I think you might see, the pattern here. This is 5,000 times this 1 plus 0.10, 1, 2, 3, 4 times over. So you can see where this little exponent comes into play. We have 4 of these 1 plus 0.10. And so what's going to happen at year 10? Well, by the time we get to year 10, we end up with this. 5,000 times 1 plus 0.1 raised to the 10th. And that gets us to one of our first formulas. And so one of our first formulas we have is what happens when you compound interest for t years, t being the variable representing the number of years. And that formula would look like this. A equals P times 1 plus R raised to the t. See what happened up here at year 10? Our principal amount, 5,000, times 1 plus the rate raised to the number of years. A represents your total amount. P, the principal. R, the APR, the annual percentage rate. And then T represents the number of years. Now, sometimes you can compound your interest, well, like more than once a year. Like not every year, but every month or every week or every day. And so if that happens, if we have our interest compounded quarterly, 4 times a year, monthly, 12 times a year, weekly, 52 times a year, etc., then this gives us a different slight take on this exact same formula, where this time we take into account n, the number of times a year we're compounding interest. And that new formula looks like this. Notice what we did is we took the annual percentage rate, the percentage rate for the year, and divided it by however many times we're compounding. So if we're compounding weekly, we would divide that rate by 52, and what that gives us is not the annual rate, but the weekly rate. But of course, if we're now looking at things in terms of weeks, we're going to have to multiply the number of years times the number of weeks. So that's why the letter n, the variable n, appears up in that exponent. And again, if you want to pause the video and write down what each one of these things means, this would be a really good time for you to take note of the formula and what's there. And don't worry about memorizing the formula. You'll be given the formula. You just need to know how to use it. Now, let's take a look at a problem. This problem is not in your notes. You have problems on the back of your notes that I would like you to try by yourself. This problem right here is simply one that you might want to write down on another sheet of paper, pause the video, and let's see if we can understand how we use our brand new formula to calculate interest or other parts of the formula. So let's say you have $5,000. You want to invest it instead of spending it. You found an account that gave you 7% interest, and it's compounded monthly, which means every month now you're going to compound that interest. And the question is, if you let it sit for 25 years, if you let it sit until you're in your 40s, how much will that $5,000 turn into? So let's take a look. First thing, here's the formula. Again, you'll always be given this formula on a quiz or test. You just need to know how to use it. So let's plug in what we know. We don't know the total amount, but we do know the principal. The principal is $5,000. The rate, we know the rate, it's 7%. So remember, you want to write that as a decimal. So it'd be 0.07. N represents the number of times you compound. So in this case, since we're compounding monthly, that would be 12. And it goes here and up here. And we're going to compound that for 25 years. So I need to multiply that 12 by 25. And now we can go right to our calculator and type this in. So one thing you have to be very careful of is your parentheses. This is 5,000 times the quantity 1 plus 0.07 divided by 12 in the parenthesis. Hit your caret button, and now if you have a fancy calculator, it automatically puts you up here in the exponent. But if you don't, you need to make sure that you're raising this entire base, this 1 plus 0.07 divided by 12, the whole thing to both 12 and 25. So it's a good idea to use parentheses, 12 times 25 in parentheses. And this is what it's telling me. It's telling me that that $5,000 can more than quintuple, and it can become $28,627.09. And that's quite a payoff. I mean, that's a pretty good payoff for just having money and choosing not to spend it, but just letting it sit. And let's look at one other problem here, and why don't you go ahead and pause the video and copy this down, and let's take a look and see how we might go about solving this. Alright, welcome back. This would be a good one to make sure you have written down, because instead of asking for how much money we have at the end, what we're asking for is how many years is it going to take for this, $4,000. I'm sorry, I forgot I changed the problem to $4,000, and turn it into $100,000. So this time, instead of looking for the A or the P, we're looking for the T. And notice that's in the exponent. And if it's in the exponent, one thing ought to come to your mind for this: logarithms. Logarithms are exponents. So let's dive in, first of all, to this formula. So there is the skeleton of my formula. And let's plug in what we know. Do we know A? Sure we do. We know A is $100,000. P, the principal, the original amount? Yep, that's right here. It's $4,000. The rate, 8%. Remember, it's got to change it to a decimal. N, how many times are we compounding it? Well, looks like right here it's weekly, 52 weeks in a year. And then T, well, T is what we're looking for, so I'm going to call that T. Just plain old T. There it is. So, here we go. We're going to have to go after T, and I notice that T is up there in the exponent, so we're going to have a little work to get to it. First off, I'm not ready to use a logarithm. Don't bring in a logarithm until you've isolated your base. So I'm going to get rid of this 4,000. It can't be here. I'm going to divide both sides by 4,000. And I get this. 25 equals that number. Let me show you where that came from. I took 1 plus 0.08 divided by 52. And I'm not going to round. I'm going to let that number sit in my calculator. And it's right there. Don't round it. Let it sit. Now is the time to bring in logarithms. So I take the log of both sides, and now that a logarithm is present, we can bring this exponent right here. We can take this exponent, we can bring it down with everybody else, because that's the power property of logarithms. So when we do that, you can now see that T is on the same level as everybody else, and to get T by itself, I'm going to have to do some division. I'm going to divide both by the 52 and by the log of that big old hideous number. Okay, we're running out of time, so real quick, what we're going to type is we're going to type log of 25, end parenthesis, divided by, and we have to capture the entire denominator in parentheses, 52 log of answer. And that gives us our final answer, about 40